So finally, we're going to hear from Dr. Xiangyu Ao from Shanghai Typhoon Institute of China Meteorological Administration, and she will talk on the impact of urbanization on meteorological conditions during landfalling typhoon Lekima over the Shanghai metropolitan area.
Okay, thank you. Hello everyone. I'm Xiangyu Ao from Shanghai Typhoon Institute of China Meteorological Administration. And it's my honor to have the chance to share my recent work about the impact of urbanization on meteorological conditions during landfalling Typhoon Lekima over the Yangtze River Delta urban cluster. Firstly, a brief introduction. Uh, Studies have shown that land surface processes are very important factors affecting tropical cyclones. A study showed that the sensitivity to surface roughness and soil moisture depends on the strength and size of the vortex. And the increasing surface roughness accelerates the decay of the strongest winds several hours of landfall, while increasing soil moisture will slow the decay of weaker outer core TC winds when it weakens to lower intensities. While storm intensity decreases with increasing surface roughness, no apparent trend in reducing the maximum gusting winds. Mechanisms are shown in the left figure as as surface frictions increases when it make landfall. So that there is the surface winds decreases, which will make the inflow angles larger. This will enhance the low-level convergence and stronger vertical motions, and this will trigger the secondary circulation that will transport high momentum along the downward to result in the stronger gusting winds. And a recent study also found that urbanization will exacerbate the total rainfall during Hurricane Harvey by a study done published in Nature. However, most of the previous studies are focused on effects on natural land surfaces, but how the cities will alter the tropical cyclone processes is still very limited. Also, to better represent urbanizations in different complexities of urban canyon models are developed. Firstly, the bulk scheme actually doesn't consider any three-dimensional structures of an urban canopy. And the single-layer urban canyon model developed by Kusaka 2001 treats the urban canyon with a simplified two-dimensional infinite length of the urban canyon with three faces: the roof, wall, and the ground. And then, but it has a limit that the lowest model level must above the building height, so limits its representation within the urban canyons. So the next more complicated building effect parameter, the BEP, or the multi-layer urban canyon model, allows several model levels inside the urban canyon. So and some momentum drag effects can explicitly represented in urban canopies. So to represent more real urban canopies. So then the model description set up the simulation case is the Typhoon Lekima 2019 made landfall at 1:45 local standard time on 10th August at the Zhejiang province, and with a very super typhoon intensity with maximum winds up to 52 meters per second. And the physical packages are listed in the middle, particularly the NOAA land surface model developed by Feichen and coupled with two different, the single layer and the BEP multi-layer are used. 3 days are simulated, and three simulations are conducted. The first one is the BEP urban with the special varying urban canopy parameters, and the BEP non-urban replacing urban cover into cropland. And a third experiment is using the single-layer urban canopy model with default urban lookup tables. And the right figure, we can see the simulated The simulated intensity and the track are well reproduced by all experiments and with small differences. And the left figure shows the innermost domain that covers studied Yangtze River Delta urban agglomeration with a very large area, including the city of Shanghai, Hangzhou, and some other cities. And the left three figures show the high resolution urban canopy morphological parameters, the building height, building area fraction, and the building surface ratio used in the model. We can see some high-rise buildings are many located in city centers, and the street width and building width are calculated by these parameters, which will influence thermodynamic processes. And this is the special temporal variations of the temperature of precipitation. And we could see the large precipitation area around 150 kilometers from typhoon center are more unevenly distributed by the two urban simulations than the non-urban simulation. And the right figure, we can see urbanization increases precipitation near coastlines, which may trigger disasters. And this is the 2-meter temperature simulation. The daytime simulation, we could see the spatial pattern are well reproduced by all experiments. And urbanization represented by urban and non-urban differences is about 2 degrees Celsius warmer. And we could see the temperature and the urban heat island decreased a lot during the second day with very heavy rainfall processes. But the urban canopy models overestimate the urban heat island and temperature during the second day. And then the nighttime temperature difference between urban and non-urban are weaker than daytime. And as the typhoon moves far away from this research area for the third day, we could see the urban heat island intensity increases a lot and just over the urban area because the wind speed is weaker without not much advection. And we could notice the simulated temperature that by the BEP is about 1 degree Celsius lower than the single layer urban canopy model. And this is a 10-meter wind simulation. This is the daytime and nighttime mean during the many influence day on 10th August. And we could see the wind speed is decreased dramatically using the BEP scheme, and the urbanization effect decreases the wind speed by about 2 to 8 meters per second over the urban area. And it seems the wind difference bifurcate along the urban area and Taihu Lake. The single layer urban canopy model doesn't show much decrease in the 10-meter wind speed. And if we look at some individual hours, we could see for the first line that the wind speed difference forms an annular type, which may be related to the cyclonic circulations of the typhoon. And if we look at higher altitudes around 900 HPA, we could see the orientation of the inner core structure is different between the urban and non-urban simulations, which may indicate that urbanization may change the asymmetric structure of tropical cyclones. And this is the daily variation of the temperature and the wind speed. We could see that the two urban canopy models is very similar in simulating of 2-meter temperatures. Both can improve the cold bias for the third day, and it is very clear that in the second day the urban heat island of the temperature is slightly overestimated. And for the wind speed, we could see the BEP scheme can dramatically decrease the root mean square area of the of the large bias of the positive bias of the wind speed is similar better than a single layer urban canyon model. And for some wind profile simulations, the left figure shows sound observing and simulated the profiles at the Baoshan station in Shanghai. We could see that the jet-like wind speed around 1 kilometer height is well reproduced, and the BEP urban scheme performs the best among the three experiments. And the right figure shows the urban area mean profiles difference between urban and non-urban, and urban and the BEP between the single layer urban canyon model. We could see the wind decrease is within 2 meters per second for the BEP scheme compared to the non-urban case, and yes, and the attenuation height can reach around 1 kilometer height. Some hours will be higher than this altitude. And the single layer mechanical model can also decrease the wind, but with a lower altitude and magnitude. And yeah, okay. Yeah, and we usually decompose the wind speed into radial and tangential wind, and its dynamic is controlled by the gradient force defined by the pressure gradient force, Coriolis force, and centrifugal force. Yeah, we could see that the gradient force depth is around 400 meters, and because of the friction velocity, there's always a gradient force inward to produce the inflow patterns. We could see the tangential wind speed is decreased a lot, and but we can see the radial wind speed adjacent to urban areas to these oceans are increased, these inflow angles. And this is by quadrant. We could see in the southeast and northeast quadrant, the inflow wind speed is increased because of the convergences. And we compared the inflow wind speed among different surface types. It can further see that the inflow speed is speed up in adjacent ocean areas. And finally, the conclusions that so I have already talked about this. So thank you very much.
Thank you so much. Are there any questions? Yes, please.
I don't know if you have seen our paper in GRL, but Pratiman Patel, PATEL, which looks at Harvey and Hurricane Florence with exactly the same thing. So I don't know how you inspired you were by that, but you may want to compare the results in that. So the same UCM, DP, UCM, all these two hurricanes, and I don't know what you're doing on the study.
Okay.
So he suggests you to read a lot of people.
Okay, thank you for your suggestions.
Compare these two studies because they're looking at the same stuff, use the same model, at different regions, right? Hurricanes.
Okay. I'll have a look.
Yeah.
Do you think which process could play a more important role in this modification? Is it like a thermal-induced effect or like a drag effect? Which one is more important for us?
Yeah. I think it's the the surface drag effect, the dynamic effect is more important than the thermal effect, because we could see the urban heat island actually disappears, even almost disappears during the rainfall periods. Yeah.
Yes.
I have a quick question. I may have missed this from your presentation. If you go back to the slide, I don't know, 3 or 4 at the beginning when you show the hurricane track, simulated by different models. Yeah, this guy. So where is the yellow line, the single UCM margin? The yellow. I'm looking I'm looking at the after the landing. So the yellow is directly overlap with black.
Yeah, before landfall is really well simulated.
Yeah. My question is after landfall.
Oh, okay.
Okay. Oh,
Oh,
I don't know.
yeah.
So this guy. Where is the laser? Yeah, here. Say here there is no much difference, right? Right here after landfall, the results diverge, right? So this is yellow. Is this yellow line? So that means the single layer using actually produce better results
Yeah.
than bad. Right.
I think there are many uncertainties. If you change some domain size or something, it will change.
I understand this, but I mean, because when you conclude, not always the bad band produces the best results. It really depends on what you look at, right?
Okay, thanks. Let's continue the discussion. Yes,
Okay.
thank you so much. Okay, with that, I want to close the session and thank all the speakers for sharing their exciting research as well. Thank you for the audience for keeping the discussion active, and have the great rest of the week.
Very good.